Hello everyone, welcome to AOS-CX 10.11 update. I'm Shobna, Technical Marketing Engineer, Aruba Campus Switching. In this session, we'll see about DODIN APL Certification update. This is the fourth session on this certification. We do our other sessions posted in our channel. This session covers following features: configuration to limit multicast forwarding cat size, support for WRED. Let's jump into the session. Let's see the agenda of this session. We will talk about abbreviations used in this session, overview of DODIN APL certification, and in-depth understanding of the following features: configuration to limit, multicast forwarding cat size, support for WRED. Abbreviations. Here are the list of abbreviations: DOD, Department of Defense; DISA, Defense Information Systems Agency; APL, Approved Product List; WRED, Weighted Random Early Detection; MSDP, Multicast Source Discovery Protocol. Let's start with the overview of DODIN APL certification. The Defense Information Systems Agency maintains the Department of Defense Information Network Approved Product List process on behalf of Department of Defense. This process provides a single consolidated list of products that have met cybersecurity and interoperation certification requirements. The DODIN APL is an acquisition decision support tool for DoD organizations interested in procuring equipments to add to the DISN to support their mission. The US government and defense organizations will only procure products that compile with DODIN APL process for the Department of Defense networks. Hence, there is a need for getting our switches certified with the DODIN APL certification. So far, we have seen about DODIN APL certification. Let's understand the new enhancements added in 10 level for upgrading this certification. AOS-CX switches operate under strict adherence to international and US government computer security standards in order to meet or exceed the demands and requirements of national agencies, organizations, and other publicly funded institutions. Most of our switches are DODIN APL certified from 10.6 release. But once a product is certified, the DoD components perform upgrades and maintenance for the life of the product to meet ongoing security requirements. Hence, these enhancements are update to the existing certification. These enhancements are mainly a host of tertiary security features required to ensure the security of our AOS-CX switches. So in this session, we'll see about configuration to limit multicast forwarding cat size and support for WRED. Let's first look into the configuration to limit multicast forwarding cat size. Let's see the overview of MSDP. MSDP, Multicast Source Discovery Protocol, is a protocol-independent multicast family multicast routing protocol defined by RFC 3618. The MSDP interconnects multiple IPv4 PIM sparse mode domains which enable PIM-SM to have rendezvous point redundancy and interdomain multicasting. MSDP uses TCP Access Transport Protocol. Each multicast tree needs to have its own RP. All of the RPs are peers directly or through other MSDP peers. The messages contain the center address and the multicast group address. When MSDP is configured in a network, the RPs running MSDP exchange source information with MSDP enables RP in other domains. And RP can join the interdomain source tree for sources that are sending to groups for which it has receivers. The RP can do that because it is the root of the shared tree within its domain, which has branches to all points in the domain where there are active receivers. When the last hop receives the device learns of a new source outside the PIM-SM domain, it can then send a join toward the source and join the interdomain source tree, which behaves similar to a local PIM register packet. The benefits of using MSDP to interconnect multiple PIM-SM domains is allows a RP to dynamically discover active sources outside of its domain introduces a more manageable approach for building multicast distribution trees between multiple domains and thus provide administrative independence and also allows filtering. The source active, that is the SA message, is a message that an RP creates and sends to the MSDP peers when it learns a new multicast source through a PIM register message. The RPs that intend to originate or receive the SA message must establish MSDP peering with other RPs, either directly or through intermediate MSDP peers. An RP that is not a DR on a shared network should only originate SAs in response to register messages it receives from the DR. It does not originate SAs for directly connected source in its domain. SA message contains the following fields: the source address of the data source, the group address the data source sends to, the IP address of the RP. The SA cache is the repository of SA messages received by the MSDP speaker. The switch always stores the received SA messages. Managing the SA cache describes the procedure that limits the size of the SA cache and the options for displaying the cache. So far, we have seen about the MSDP and then the SA message and the SA cache. So let's see why there is a need for this enhancement configuration to limit the multicast forwarding cache size. This enhancement has a SA limit command to limit the overall number of source multicast group entries that a device can accept from the specified MSBS and store in the SA cache. So the main requirement for this enhancement is to protect our switches from denial of service attacks. So the switches cannot receive more than the configured SA limit. So if the command is configured, the device maintains the per peer count of S, G messages stored in SA cache and will ignore the new SNG from a peer if the configured SA limit for that peer has been reached. Also, as an intermediate MSDP router, the SA packets received from the peer gets forwarded to other peers as it is and updates this SA cache as per the configured limit. So it will be really helpful in protecting our MSDP enabled devices from the denial of service attacks. Let's see the guidelines and best practices to be followed for this feature. At any point of time, the overall SA limit across all peers, even across all VRF, should not exceed the system capacity for respective platform. So in the next slide, we'll see about platform-wise SA limit. And next is, if SA limit configured is greater than the current limit, it will accept additional S, J entries from the next SA message and add it to the cache. And if the SA limit configured is less than the current limit, the SNG entries exceeding the current limit will be removed after the SA cache timeout. So when the SA messages are received, the SA cache timeout are refreshed for the existing S, G cache entries on a first come first serve basis till the configured limit is reached. So this will help in restricting the SA cache size to the configured limits. Let's follow these guidelines when we are using this enhancement. Let's see the SA cache system limits. So this is the overall system-wide limits for this platforms. For 10K, it is around 8K. For 9300 platform, it is 8K. And for 8400 platform, it is 16K. For 8360, it is 8K. And for 8325 as well, it is 8K. And for 8320, it is 4K. And for 6400 platform, it is 8K. And for 6300 platform, 8K. So all these platforms supports MSDP, and these are the system-wide SA cache limit. And we can also configure the peer SA limit as we discussed about this in our enhancement. Configuration and show command. To configure the SA limit peer level, we need to go to the router MSDP concept, and inside that there is IP MSDP peer and then the peer address. There resides our new configuration SA limit. So we can configure the SA limit with range of 0 to 65535. So this 65535 is the highest SA cache limit, and it will vary from platform to platform. So as we have seen in the previous slide, the SA cache limit varies from platform to platform, and based on the SA limit also will varies the platforms. So once we have configured this SA cache limit, to view the configured SA limit, so we need to go to the show IP MSDP peer, and then view the SA limit configured. Since a peer level command, we need to use this peer level show command as well. So once we have configured and using this feature, if we wanted to do any debugging or troubleshooting or any issues with respect to these features, the debug MSDP all has to be enabled, and then the debug can be redirected to either the console or even the buffer or for the syslog. So once this debug is enabled, all the MSDP related debug messages will be displayed in the debug logs. So this is also an enhancement with MSDP. Hence, with the debug MSDP all, we can see the SA limit configuration changes as well. Next comes the diagnostics. So if we wanted to make sure whatever you configured in the MSDP SA limit, is it internally configured the same as well, we can use this diagnostics diagram MSDP basic. So once we do this command, it will display the peer level configurations. And this is a snippet of the diagram output for the MSDP basic. If you see here, for the particular peer, it will display the configured SA limit. So we can make sure whatever that is configured in the CLI, it is reflected internally in the switch as well. Let's see the parities. So we have done the parity analysis with the third-party switches and then our own AOS switches. First comes the AOS. So AOS switches does not support MSDP, so this feature is also not applicable for the AOS switches. Next comes the S3C switches. So MSDP is supported in S3C switches, and even in S3C switches, we have peer level configuration to limit the SA catch limit. So we have the configuration as peer, and then the peer address, and then the SA catch maximum SA limit. And here comes our third-party competitor, Cisco. So MSDP is supported in Cisco switches, and even in Cisco switches, this is a peer level configuration that can be configured using IP, MSDP, SA limit, the peer address, and then the SA limit. Let's jump into the demo. So let's see the topology for the demo. I'll be using 3 switches in this topology. So the peer 1 is connected to peer 2 via MSDP. Similarly, peer 3 is connected via peer 2 for MSDP. And peer 1 and peer 3, I have the multicast source streams running with XCR sources. So the source for peer 1 is 20.0.0.2 and multicast group address 238.1.1.10. And for the peer 3, I have a source address as 50.0.0.2 and the multicast group address as 239.1.1 to 10. So all these peers has its own RP. So if the peer 1, the RP is 1.1.1.11, and for peer 3, the RP is 3.3.33, and for peer 2, the RP is 2.2.22. So from the peer, there will be joins coming from the XCR receiver. So now the SA messages will be coming from the peer 1 to peer 2, similarly from peer 3 to peer 2. Let's see how the SA messages can be limited in this feature. So I open the controls of all the peers here. So they are in version 10.11. So if you could see here, the MSDP has been successful. Show IP, MSDP, summary. We have the, from the peer 2, you can see the peer 1 and peer 3 has been connected and they are up. So now let's see from peer 1. Show IP, MROD. So if you could see, we are sending 10 entries, S, J entries from peer 1. Similarly, ten entries from peer 3, XCR sources, multicast sources. We'll go to peer 2 and check the SA catch messages. Show IP, MSDP. If you could see here, there are totally 20 entries. So the first 10 entries coming from peer 1 with source as 20.0.0.2 and multicast group address ranging from 238.1.1.1 to 10. And similarly, 10 entries coming from the peer 3 with source as 50.0.2 and multicast group address ranging from 239 1.1.1 to 10. So now we have 20 entries. So let's configure our SA limit configuration to limit this entries. So I'll go to the router, MSDP, contest, and this configuration is per peer configuration. So I visit the particular peer. And here comes the configuration. So here there is a range of 0 to 65535, but 65535 is the higher end SA limit, but it differs from platform to platform. You could see here, you try to configure it, it will say it exceeds the system capacities. So maximum the SA capacity allowed for this model is 4096. So based on the switch model, the SA limit cat size will vary. So let me configure the SA limit as 5. Save the configuration. So let's see the SA catch now. So currently it is 20. So once this message is timeout, the next time from the peer 1, it will receive only 5 messages. So now we could see only 15 entries here. Only 5 entries are accepted from the peer 1 and 10 entries from the peer 3. So the entries from the peer 3 are not disturbed because we have not configured any SA limit for the peer 3. We have configured the SA limit only for peer 1. So only the peer 1 SA limit has reduced from 10 to 5 here. So this is a peer level configuration that helps to limit the SA messages from the particular peer. So now let's unconfigure the configuration and check whether it is back to the normal form. So again, I'll go to the router, MSDP, IP, MSDP, peer, 1.1.11, give no SA limit. So we'll wait for the SA messages. So now let's see it. Now we could say all the 20 entries are learned. So the 10 entries are learned from the peer 1 and then 10 entries are learned from the peer 3. So this feature greatly helps in limiting the SA messages from the peers and helps us from the DOD kind of attack. So let's see what is the debug available for this feature. So we can enable debug, MSDP with submodule as all with CVRTS debug. So once we enable this debug, we can clearly see the SA limit configuration changes. So if you could see here, it says SA limit changed to 5 on this peer. So any SA limit changes will be automatically reflected in the debugs, and based on the SA message limit, those SA messages only will be accepted by the switch. So this debugging also greatly helps in identifying the SA limit configuration changes. Hope everyone understood this feature. Try to implement this MSDP SA limit configurations to protect our switches from the DoD attacks. Let's see the next important feature, support for WRED. Let's see the overview of WRED. Before we see that overview of WRED, we need to understand what is TCP global synchronization and how WRED helps it solving the problem. TCP global synchronization occurs when a sudden burst of traffic causes simultaneous packet loss across many TCP sessions using a single link. Each affected TCP session backs off its send rate at the same time, causing link utilization to go way down. When the link utilization is down, the packet loss is low, and therefore each affected TCP session increases its send rates at the same time, causing link utilization to go way up and causing severe congestion again, and this cycle repeats. So the result is a sawtooth shaped bandwidth utilization on a single link, causing inefficient use of available bandwidth and then the throughput. The leading cause of TCP global synchronization is a sudden congestion causing numerous packet drops and simultaneously affecting many TCP flows all at once, as would typically happen in a classic tail drop queue management. More intelligent queue management such as WRED is designed to improve the overall network performance by avoiding these numerous and sudden packet drops that can cause TCP global synchronization. Let's see about WRD in our coming slides. Let's see more details about WRED. WRED stands for Weighted Random Early Detection. It's a queuing discipline for a network scheduler suited for congestion avoidance. It is an extension to Random Early Detection (RED), where a single queue may have several different set of queue thresholds, and each threshold set is associated to a particular traffic class. For example, a queue may have lower thresholds for low priority packet. A queue buildup will cause lower priority packets to be dropped, hence protecting the higher priority packets in the same queue. In this way, the quality of service prioritization is made possible for important packets from a pool of packets using the same buffer. It is more likely that a standard traffic will be dropped instead of a higher prioritized traffic. And it has been implemented to support RFC 2597, and drops are randomized in order to avoid potential synchronization between multiple streams. Let's see more details about WRD in the coming slides. Let's see the WRED workflow. WRED avoid global TCP synchronizations by randomly dropping the packets. When the sending rate of some TCP sessions slow down after their packets are dropped, other TCP sessions remain at high sending rates. The link bandwidth is efficiently used because TCP sessions at high sending rates always exist. The WRD algorithm sets an upper threshold and then a lower threshold for each queue and processes the packets in the queue as follows. When the queue size is shorter than the lower threshold, no packets are dropped. When queue size reaches the upper threshold, all subsequent packets are dropped. When the queue size is between the lower threshold and the upper threshold, the received packets are dropped at random. The drop probability in a queue increases along with the queue size under the maximum drop probability. The advantage of WRD is it is DSCP aware and will drop the lower precedence traffic first. So it uses differentiated drop policies for different IP precedence values, and packets with lower IP precedence are more likely to be dropped. If the current queue size is compared with the upper threshold and lower threshold to determine the drop policy, the bursty traffic is not fairly treated. To solve this problem, WRD compares the average queue size with the upper threshold and lower threshold to determine the drop probability. So far, we have seen about the overview of WRD and how WRD works. Let's see the major use case of WRD. The major objective of WRD is for providing a better link utilization. Let's see with an example how WRD works. So here we have a graph. The x-axis represents the queue utilization and y-axis represents the drop probability. The WRD monitors the average queue depth. When the queue starts to fill, it will only drop a few random packets. When the queue length increases, it becomes more aggressive and drops even more random packets until it reaches a certain limit. When this limit is reached, all the packets will be dropped linearly. So in this example, we have a minimum threshold of 25 and maximum threshold of 65 and drop probability as 40%. That is the chances in percentage that WRD will drop our packets. So when the average queue depth is below the minimum threshold 25, WRD does not drop any packets at all. When the average queue depth is above the minimum threshold 25, the WRD starts to drop the small number of random packets. When the average queue depth even further, the WRD drops a larger percentage of random packets until we reach the drop probability and then the maximum threshold. When the average queue depth reaches the maximum threshold 65, WRD will drop all the packets. This drop probability is the number of packets the WRD drops when we hit the maximum threshold of 65. So the WRD works in this way. If the drops are occurred on all streams at the same time, multiple senders might respond by backing off the transmit rates and then ramping up again. In such synchronized behavior causes link utilization to fluctuate between high and low and wasting this bandwidth. So WRT helps by randomly dropping and ensures that only some streams detect drops and that they detect at different times. This results in better link utilization as some senders continue to transmit at a higher rate while others back off and ramp up again. Thereby, WRD helps in better link utilization. Let's see the WRD support matrix. So the WRD feature is supported in all of these below platforms. But platform-wise, there are differences in WRD support. First comes the WRD max probability. This WRD max probability is a configuration to define the drop probability. So this configuration is available only in 10K, 9300, 8400, 8360 V2, 8325, 8320 and 6400 V2 platforms. In other platforms, we do not have this WRD max probability setting. And next comes the WRD traffic. So WRD protocol can be either applied to the responsive traffic like TCP traffic, or it can be applied for the non-responsive protocols like UDP. So here we can control for which type of protocol we wanted the WRD congestion avoidance to happen. Either it is for the responsive protocols like TCP or for the non-responsive protocols like UDP. So for that, we do have CLA configuration to differentiate as WRD responsive and WRD non-responsive. So such kind of representation is available in all the platform except 8400. So for the 8400 platforms, we do have only a WRD generic configuration that will be doing the WRD in all the traffic types. Here comes the configuration for WRD. Let's see the configuration task list for the WRD feature. First, we need to create a threshold profile defining one or more queues. The threshold configurations with WRD action will be applied. So we need to go to QoS threshold profile and mention the name of the threshold profile. So once we configure it, we will be in the QoS threshold profile context. So in this context, there will be option to configure this WRD based on the queues. So we have to mention in which queues, like if it is a Q1 or Q2, and then the action as WRD responsive or WRD generic or WRD non-responsive. Like if we wanted the WRD to be applied only for responsive protocols, we have to mention as WRED RSP. And if we wanted the WRD to be for the non-responsive protocols, we have to mention WRED non-RESP. So if the platform does not differentiate between the responsive and non-responsive traffic, we have only the WRED as the action. So once we mention this action as WRD, next we need to mention like for which color traffic we wanted to apply this WRD profile, whether it is red, yellow, green. So once we mention it, we need to specify the minimum threshold as percentage in platform that support percentage or as a minimum threshold in kilobytes. And then the maximum threshold similarly as a percentage or in kilobytes. So once we mention it, there is an option to configure the maximum drop probability. So that can also be in percentage. So once we have configured all this, we have to apply this threshold profile to the interface. So once we have this configured, we need to go to the apply QoS threshold profile. It can be done either globally. So once it is configured globally, it will apply to all the ports in the switch. Or we can go to the particular interface and then apply this QoS threshold profile. So once we have configured the WRD configurations, we wanted to check how the configuration is made. You can use the show command, show QoS threshold profile to view the WRD configuration. We have to mention show QoS threshold profile and then the name of the profile. So here it will display the queue, and then what is the WRD action configured, and which type of traffic, that is the green, red, or yellow type of traffic this is applied, and what is the minimum and maximum threshold, is it in percentage or kilobytes, and then the maximum probability, it will be displayed clearly here. And it will also display in which are the ports this QoS threshold profile is applied. So if you wanted to view the drops rates, you can use the show interface, the interface numbers and the queues. So here it will display the queue specific TX bytes, TX packets and TX drops. So thereby we will be able to identify how much packets are getting dropped, and we can also see the TX byte depth. So we have seen the configurations and show commands. If we face an issue with this WRD configuration, what type of troubleshooting we can do? First, we have to enable the debugging. So this is a feature under the QoS umbrella. So it is enabled with debug QoS all, and by default it is severity debug. So here it will display the debug log related to the WRD configurations. Next comes the diagnostics. So if you face the issues like you have configured the CLIs, but it's not getting effective, then we can use this diagram QoS basic to view whether the configurations which we are done via CLI is it applied internally in the switch or not. Next comes the guidelines. These are the guidelines that need to be followed when we are configuring and applying the WRD profiles. The WRD threshold action will randomly early drop packets to signal congestion. So more than one WRD action can be configured on single queue for different packet colors like red, green, and then yellow. If a threshold profile fails to be applied for any reason, its status will be shown in show QoS threshold profile as not applied, in which other ports it has not been applied. When applying the global threshold profile, make sure the name threshold profile already exists. If the name profile does not exist, the application of the threshold profile will be ignored, and we need to again configure the profile and apply it back. Next comes the parity analysis. Let's see whether this feature is supported in other switches. First comes our own product AOS. The WRD feature is not present in our AOS switches. Next comes S3C. S3C switches support WRD feature. So we have the configuration device level as QoS WRD Q, and then the table with the drop policy. Here we can mention the drop policy as which queue, the drop level, and then the low limit of threshold and higher limit of threshold, along with the drop probability. They mention it as a discard probability. And it is also present in Cisco switches. So here we create a class map and then the policy map. In the policy map, we'll mention the bandwidth percentage, and then we can also mention the how much is the random detect policy, whether it can be percentage of minimum threshold and then the maximum threshold, and how the random detect happens. Is it based on the DSCP? So far, we have seen about WRD feature. Let's jump into the demo and we'll showcase how WRD feature can be enabled, configured, and then how it works. So for this demo, I'll be using the below topology. There will be two XCR sources that will be sending QoS traffic to the destination. So here I'll be sending three color traffics. So the first one is green. So it will be having the DSCP values and then the code point 18 and assured forwarding 21, and it will belong to Q2. So next comes the yellow traffic. So it is having the DSCP value code point 20, Q2, and then assured forwarding 22. And next the red traffic, that is DSCP code point value 22, Q2, and then assured forwarding 23. So these traffic will be sent via two ingress ports, and it will be egressing via the third port. And we'll be doing oversubscription of traffic from the two ingress ports, so that the egress ports, the dropping of the packets we can see based on the WRT configuration. So let's see the demo. For this demo, I have used a AOS-CX 9300 box. This is currently under default configurations. So let's see from scratch how WRD configuration can be enabled. So I have three ports, two ingress ports, and third one is the egress ports. So let us do the configurations. We could see here it is currently in 10.11 version. So first, let me create a VLAN and assign a VLAN the IP address. So I will enable this VLAN as a tagged VLAN in the ports. So let me disable routing. Then no shut the ports. So let us check if the ports are up. So the ports are up now. So now let's configure the WRD profile. So before we configure the WRD profile, we have to trust based on the QoS as DHCP. So why we have to trust based on DHCP is the traffic we are planning to send is via the DHCP code point values. So show QoS DHCP if you see here. As discussed, we'll be sending the traffic with code point 18 that belongs to green color traffic AF21, and then code point 20 that belongs to yellow traffic and AF22, and then code point 22 so that belongs to red traffic in AF23. So these will be sent in the Q2. So the WRD configurations will be effective only the Q2 here. So to configure the WRD configurations, we need to create a threshold profile, QoS threshold profile. So I'm naming it as a WRD underscore test. So here we have to configure this based on the queue. The traffic which we are sending belongs to Q2. So the WRD configuration has to be enabled for the Q2. So here there are different types. So the first one is ECN, and second one for the WRD, we have non-responsive and responsive. As discussed earlier, non-responsive is for non-responsive protocols like UDP, and responsive is for responsive protocols like TCP. So in this demo, we'll be using WRD responsive type. So we'll be sending the TCP traffic. So here comes the traffic color based. So which type of traffic do you wanted this WRD action to be implemented? So we are planning to do it for all the three colors. So first comes the green. Here comes the minimum threshold. So we need to specify the minimum threshold. So I'll configure the minimum threshold as 45K kilobytes. So next comes the maximum threshold. So I'll specify the maximum threshold as 50K bytes. And next comes the maximum drop probability. So I'll configure as 60%. So it is ending with percent. So we can view the configurations using show run current context. So this is the configurations we have made currently. For the Q2, we have applied action as WRD responsive for the green traffic with minimum threshold as 45K kilobytes and maximum threshold as 50K kilobytes and maximum probability as 60%. Similarly, we will configure the minimum maximum threshold for the yellow and red traffic. So now I'll be doing for the yellow traffic. And next for the red traffic. If you could see the configuration currently for the QoS threshold profile. So here is the configurations for the green, yellow, and the red traffic, where the minimum threshold is varying from 45 to 50K kilobytes. And then for the yellow traffic, it is varying from 30K to 40K kilobytes. And for the red traffic, it is varying from 10K to 30K kilobytes. And maximum probability of drop is set as 60% for all the colored traffic. So once this configuration is made, we can apply this QoS threshold profile globally using apply QoS threshold profile, and then that threshold profile name. So you can either apply globally or the egress interface where we wanted to apply it, like interface 113 QoS apply QoS threshold profile WRED underscore test. So this QoS threshold profile can be either applied globally or can be applied even in the particular interface. So now we have applied the configurations. So we can check how it works now. For that, we'll go to the Ixia and generate the traffic. So let me share the Ixia screen now. So this is the Ixia where we have 3 ports. 2 will be the ingress ports and third port will be the egress port receiving the traffic from these ingress ports. So the traffic will be sent from this port 1 and port 2 to port 3. So here we'll be oversubscribing the port 3 by sending the maximum traffic from both port 1 and port 2. And all the 3 ports are of 40 gig capacity. So let's go to the traffic. So I'm creating a traffic new stream. So I'll be selecting port 1 and port 2. From that, the traffic will be received in port 3. So next is, it will be unidirectional traffic. So next I go to the packet type. So here I'll be adding a TCP header. So currently it is only till IPv4. Since it's a responsive traffic, we are planning to add a TCP header. So added the TCP header, saving it. And again going to the packet editor. So here I'll be adding the DHCP values in the IP header. So I'll be using the IP priority as differentiated service. So here I'll be expanding that differentiated service, and then we'll be changing the default PHP values. So here we have to add the code points 18, 20, and 22 for the green, yellow, and red traffic. So I'm creating a list with those values 18, 20, and then 22. So here's a list with 18, 20, 22 traffic. So next is the flow group settings. So I'll be tracking the flow group based on source destination endpoint pair and then the default PHP. So currently the line rate will be around 20% I'll be sending. Next, the flow has been tracked using source destination endpoint pair and then the default PHP. Let's see the flow groups. So the flow groups has been created now. So we'll validate the flow groups. So from the port 1 and port 2, they will be traffic sent to the port 3 here. So all of them will be using around 20%. So let's see the traffic flow now. So I'm applying and starting the traffic here. So we'll wait for the statistics to be created. So the flow statistics now created. If you could see here, from the port 1 and 2, there will be traffic sent to the port 3. So with the default PHP values 18, 20, and 22. So it's from these endpoint paths. So currently there's not much loss in the traffic. Everything is going fine. So let's now increase the traffic rate to check the loss percentage, how the loss is happening when we do the oversubscription. Currently it is subscribed correctly. So go to the flow groups. Now I will increase it to 50%. First, let's increase to 40%, then we'll increase to 50%. The traffic has increased. Now let's see the queue depth. So if you see the show interface queues, it will show the TX bytes for the particular queue for the egress interface 113. We can see the TX bytes and TX packets. Currently, there is no TX drop since we have not yet oversubscribed, and we need to watch this TX byte depth. This is the buffer depth for this particular queue. So we have to check based on our QoS threshold profile, this buffer depth will vary. So the first buffer depth reaching the minimum threshold is the red traffic, where if the buffer depth is around 10K kilobytes, we will start seeing drops for the red traffic. So let's try to increase this buffer depth. So we'll increase the traffic percentage. So let's see the buffer depth if it's increased. Yeah, it is increasing to this amount. So we'll wait for it to increase majorly. So let's see the buffer depth now. So the buffer depth is now has reached. So this is in bytes. So if you can skip the last three, this is around 30K now. So we'll see the drops, right? The drops percentage you can see. If we could see for the drops, now the buffer depth has increased gradually. So we'll see how much is the drop for the particular colors. So there is minimum drops for the 18. The 18 traffic is minimum drop, that is green color traffic is minimum drop. And next comes the yellow traffic 20. So for that there is a drop percentage loss of 0.127. And if you see for the red traffic, the drop percentage is more because you see the QoS threshold profile. The minimum threshold is around 10K bytes, and then the maximum threshold is around 30K bytes. And the maximum probability is 60%. Since now our buffer depth has increased to 30K bytes, the red traffic will be the one suffering the major loss, and then the yellow traffic, and then the green traffic, because the yellow traffic, the minimum threshold is around 30K bytes, 30K kilobytes, and for the green traffic it is around 40K kilobytes. So we'll try to increase the traffic further, and we'll see the traffic drop mode will seen for the yellow traffic now. So we'll try to increase further to 70%. So let's see the buffer depth now. It has not yet increased. We'll wait for a while. So now if you could see here, the red traffic loss percentage is more, and even the yellow traffic drop percentage is more. And now the green traffic loss percentage has started gradually based on the traffic increase. So let's see the buffer depth now. We'll try to increase further. I'll make it around 75%. So now we could see the loss percentage is gradually increasing for the traffics. So let's increase to 80% now. So we could see here, now the yellow traffic is seeing more drops. So even the buffer depth has increased. So once the buffer depth is reaches the $45K kilobytes, then we will see more traffic drop seen in the green color traffic. Currently, it is around 33K kilobytes. So only the yellow and red traffic are seeing major drop. But the green traffic, since the minimum threshold has not yet reached, it was not seeing any drop. So let's increase the buffer depth by increasing the traffic percentage. So it came around 30K kilobytes. So let's increase further. So now it is around 39K kilobytes. Now I'll increase to 100%. So still now it is around 40K kilobytes. So that's the reason we are not seeing major drop in the green color traffic. So the maximum drop probability is around 60%. That's the reason. So we are not seeing the full drop happening for the other color traffics like red and yellow. So we are seeing only the minimum drop happening. So this is how our QoS WRED feature is working. So if you wanted to check the show command, what is the queue configurations, you can use the below show command. Show QoS threshold profile. So it will list the threshold profile. And then based on threshold profile name, also we can see the output. It will, since we have globally applied this threshold profile, so it will show all the ports where the threshold profile is applied. And it will also mention the configuration of the threshold profile. For any diagnostic related information for this feature, you can use diagram QoS basic. So it will list the configurations of the WRD, like, so now it will display which is the WRD profile configure. So globally we have used this WRD profile. So here we can see the minimum kilobytes and maximum kilobytes threshold values, and then the probability configure. So this diagnostic demo will help us to identify these configurations. So now we have come to the end of the demo session. Thanks everyone for watching this recording. If you have any further queries, do post your queries in our AREDS community.